Hello everyone. Let's follow up the lecture that I just posted on lubrication theory, where I talked about the scaling analysis, right, to simplify the Navier-Stokes. And let's work on some problems that we can solve, right? These are the problems directly from the book. And I'm just going to go through the book and provide you with some additional help, right, where I think it might be necessary. Okay, so the problem is consider the steady flow in a 2D channel that narrows gradually in the direction of flow. Okay, so the walls are not necessarily planar. Okay, that's fine. Given the volumetric flow rate and the local half height h of x, right? The objective is to determine the velocity and the pressure. So the objective is to determine Vx as a function of x comma y and p as a function of x, right? The goal is to determine these. Okay, so now how do you go about doing that, right? So what is a volumetric flow rate? So first, note this very carefully. It is the local mean velocity is u of x, right? U of x is the local mean velocity. So that's very important. It's the mean velocity, and that mean velocity is a function of x. Makes sense, right? I mean, as you go along in x, the cross-sectional area changes. So if the mass flow rate is to be conserved, then the mean velocity has to change, right? Obviously, so as the cross-sectional area decreases as one goes along in x, then obviously the mean velocity has to increase. So how do you determine the volumetric flow rate? I mean, look at that. The factor 2 is basically is the top and bottom, right? Two sections, zeros right in the middle. So 2 times, what is the volumetric flow rate? Volumetric flow rate is nothing but velocity times cross-sectional area, right? Cross-sectional area is nothing but h times w. And what is given here is actually the volumetric flow rate per unit width, right? So again, as we discussed in class, imagine that you are the fluid. Look in front of you. What is the cross-section that you're seeing? And the cross-section that you're seeing is, is nothing but the width is w, and the height is nothing but h of x. So the cross-sectional area is w times h of x. Area times velocity is volumetric flow rate. Okay. So excuse me. So please go through this book, the problem in the book. So again, there are two conditions. Remember, when we discussed the constraints for lubrication analysis, they were Ly over Lx is much less than 1. That's the geometric constraints. And the dynamic constraints involves a Reynolds number Re times Ly over Lx is much less than 1. So these are the two constraints that are to be valid. I mean, it is very obvious. I mean, look at this. So this is geometric constraint, and this is the dynamic constraint. Okay, so now start off from the Navier-Stokes, right? What is the Navier-Stokes? I mean, look, mu times dou squared Vx divided by dou y squared is equal to dou p over dou x, right? Is equal to dou p over dou x, correct? So now integrate with respect to y 2 times, right? And this is what you get. Then again, where C1 and C2 are the two constants. So now what are the boundary conditions? Now this is so obviously at y equal to plus minus h, the velocity is 0. That's the walls, right? So two boundary conditions determine C1 and C2. Please work it out yourself, right? This is important. Please work it out yourself. And then you'll be able to, you'll have more confidence. So once, so apply the boundary conditions, get C1 and C2. Once you get C1 and C2, you know, obviously, determine what the pressure gradient is, right? From one of the constants, right? I mean, look at that. I mean, what constant is this? I mean, at y equal to h, right? I mean, yeah. So so determine what the constants are, then plug it back into the equation. Okay, so voila, yeah, that's your Vx is a function of both x and y. So please work out the math and convince that this equation is right. I mean, this is in your best benefit. I mean, okay. So now you get Vx as a function of y, right? Now, how do you get Vy? For that, you use the continuity dou Vx over dou x plus dou Vy over dou y is equal to 0, right? What is the continuity? Del dot V is 0. So basically now all I need to do is dou Vy over dou y is minus dou Vx over dou x. Integrate with respect to y. So voila, right? So look at this. So now what is, so obviously this is at the value of Vy at y equal to 0. I mean, so why is that? Now what does symmetry say now, right? So this is Vy when y equal to 0, right? So basically, I mean, think about it this way, right? I mean, they are the walls at the top and bottom, right? So this is Vy. If this is Vy, so Vy can either be this way or it can be this way, right? So if it is symmetrical about the center line, then Vy at x, at any x, at y equal to 0, which is the center line, has to be 0, right? So this value is 0. So this is the value of Vy at x comma y. So it's all math. I mean, you should be able to do this. I mean, please convince yourself, work out the math and convince yourself that this works out, right? Okay, so okay, so now how is the pressure? How do you calculate the pressure? Now, obviously, I mean, look at this. For pressure, you can use the above equation, right? So using, so obviously you just have to integrate that. So integrate from x equal to 0 to L, right? Which gives me the value of the pressure drop, right? As you flow along the tapered channel. So now, obviously, now if you want to calculate what the pressure drop is, across this tapered channel, obviously you need to know how H changes as a function of X or the taper, right? The geometry. If you assume that it just goes linearly with distance, plug it back in and you can get to an analytical expression for the pressure drop. Okay, that's it. Simple, right? I mean, look, again, coming back, pause, right? I mean, look, continuity is obviously valid. That's a mass balance, right? Mass balance states that first step dou Vx over dou x plus dou Vy over dou y is 0. In this particular problem, there's both a Vx and a Vy, and both are functions of x and y. Now, this is obviously a very small channel, right? The width of the channel is small. So, and then the flow is also not very fast. So in this particular instance, the geometric constraint and the dynamic constraint are valid. So basically, you get the Navier-Stokes simplifies to the lubrication approximation, right, shown here. Now, obviously, integrate it twice, solve for the velocity, you get an expression for the pressure. P is just a function of x in the lubrication approximation. Once you get Vx, use the continuity to get to Vy. Once you solve for Vy, you can also solve for the pressure drop. And to solve for the pressure drop, you need to know how the taper distance changes as a function of x. If you assume some simple mathematical whatever, I mean, way in which it changes, say it's linear, then you can calculate what the pressure drop is going to be. Okay, so now there is another problem. This is also a very nice problem. I mean, and as you can see, so basically, I mean, like say gears, I mean, and say even in the chemical industry, semiconductor industry, there's a mechanical polishing. I mean, there are a number of instances where a pair of solid objects are separated by a thin film of liquid, right? Such as an oil. Any moving parts, number of moving parts in your cars, planes have, I mean, the situation is encountered. So typically, as the book says, there is a relative motion between the objects. So in such cases, I mean, there can be rotation on top of the fluid flow. So of particular interest in all these are the forces generated, right? So what force does I mean, when you have a liquid that is squeeze flow, and then this is what is known as squeeze flow, right? This is a very small gap through which the liquid is flowing, obviously. And then when you're trying to pump liquids, the liquid also obviously exerts a force on the top surface. So it is of our interest to figure out what this force is, right? So you need to, yeah. So the question is, how do you calculate that? Okay, so now basically as shown in figure 7.1, the surfaces are assumed to be separated by a distance, h of x, right? The coordinates are chosen. So basically the upper surface is stationary, the lower surface is moving at a velocity u, right? Now the pressure is specified at two locations. You know the pressure at x2 and you know the pressure at x1, right? So delta P is P2 minus P1. Okay, so now the velocity in the gap. So basically, okay, so now you can start off with, obviously with the lubrication approximation, which states dou P over dou X is mu times dou squared Vx divided by dou y squared. Again, integrate this twice. The boundary conditions are at y equal to 0, the velocity is u. At y equal to h of x, obviously the velocity Vx is 0, right? At y equal to 0, the velocity is u. So obviously, two boundary conditions solve, convince yourself that you get to the expression for Vx as a function of y, okay? So now, so obviously, right? Okay. So now, how do you get the volumetric flow rate, right? Now you get the Vx as a function of y. Now, once you get Vx as a function of y, how do you calculate the volumetric flow rate? The volumetric flow rate is nothing but again, right? Imagine you are the fluid. What cross-sectional area do you see in front of you? This is the volumetric flow rate per unit width. And so Q is nothing but H of x times now excuse me, 2 times h of x times u as a function of x, where u is nothing but the mean velocity, right? How do you calculate the mean velocity? This is nothing but 2 times h of x is nothing but 1 divided by h of x times integral 0 to h vx dy. Okay. Okay. So sorry. In this case, it is not symmetrical. Sorry. The zero is at the bottom, so there is no two in this particular problem. That's a mistake. So Q is the volumetric flow rate is now per unit width is nothing but 0 to h Vx dy, right? Which is what is given here. You have just calculated Vx from the Navier-Stokes. So now you can integrate to get an expression for Q. Again, please work out the math yourself. Okay, so now obviously, so you have Q in terms of you can rearrange, get an expression for dP over dx, right? So that is done. So now you can plug it back in if you want, and then you can get Px as a function of x comma y. Instead of dP over dx, you get Q, right? So you just some rearranging and playing around with the math. So now, okay, so now, okay, so now you get Vx as a function of x and y. You can also, if you want, get Vy as a function of x and y. For this, obviously, use the continuity equation. And why do you, so another advantage, obviously, in calculating the velocities, obviously, you can calculate what the pressure drop is, which is what we just did. On top of it, you can calculate the derivatives, right? How dou Vx over dou x. You can also calculate dou Vx over dou y. Why do you need to calculate all this? You can calculate all this because you can get the shear stress, right? The shear stress is obviously related to the gradient in velocity, right? So tau yx, right? Why is there a shear stress in the x direction? Because because the velocity in the x direction changes as you go up in y, right? Vx is a function of y. So there are different layers of fluid moving at different velocities, as a result of which there is a shear stress. Once you calculate the Vx from the Navier-Stokes, you can take the derivative and you can calculate what the shear stress is going to be. Okay, so so basically, I mean, look, so there is a lot of math. I'm sorry, you just have to plug in the math. Again, you have calculated what dP over dx is. Once you calculate what dP over dx is, you can integrate and you can get what the pressure is going to be. And it comes to all sorts of, and you can come to all sorts of conclusions based on that, right? Okay, so basically you can do that. Please work out the math. I mean, let's just focus on the math here. I mean, there are a bunch of physics in here as well, which I will get to in the once you calculate these quantities, right? So then the question is now, how are you going to calculate the forces, right? And then let's look into that in the next video.